So we talked about the quiz. And so today I'm going to continue with eigenvalues and eigenvectors. So eigenvectors and ODEs. I guess this is part 3, huh? This. Thing. Okay, so again, the motto is to expand so again, let me write down the objectives. So understanding eigenvalues and eigenvectors. Vectors. And understanding how to solve ODEs. Okay. So the model that we were talking about is how expanding in a basis of eigenvectors is easy. So first I want to say that, so I want to show you something that you maybe have seen before, is that, the problem of solving any higher order ODE in one dependent variable can be reduced to a system of ODEs in first order, which is first order. Okay, so let me write down an ordinary differential equation in one variable. So what we're going to do is we're going to convert let's call this this is an n. So we can say A0 T Y. So we'll have something like this. And then we can have some initial values. So let's say we take some initial values. And then we'll go y prime. Let's do it like this, dy dt. At 0, this will be y prime of 0, and so on. And then we'll go y to the n minus 1 of 0, or let's do it like this, dy dt. This is n minus 1 here. This will be y n minus 1, 0, something like this. Okay, so we have this. This is an initial value problem. So we specify initial values. Okay, and we convert this into, so we convert to a system of ODEs. Maybe I already did this, so dy dt here, a of ty, like this, where we do y of 0 is some vector y, not like this. Okay, and here, so y is y1. I guess we could write it as y1 through yn, like this. Okay, so or maybe we could put a transpose here. So it's a column vector. Okay, so this is this is a higher order system in one variable, and then this is a first order since there's only one derivative appearing in many variables, so many dependent variables. Okay? So the process goes like this. So okay? So what we do is we just declare new variables. Okay? So we have, I don't know, we could say, so we say y, so this is going to be y1, okay? And then we have dy dt, this is y2, and so on and so forth. So this is like, you don't want to say like this is, sometimes people write velocity when it's second order, d squared y, dt squared, so this is y3, etc. Okay? And then you have dn minus 1y dt to the n. And so this will be yn, like this. Okay, so now we have these new variables. So here are the new variables. And now, okay, so now notice that we get a differential equation for them. So the system of differential equations becomes this. So y1, so let's do it like this. So dy1 dt, so this is y, so this is just y2. y2. dy2 dt, right? And this is equal to y3, etc. Okay, until we get to dyn minus 1 dt. So this is yn. And then we have dyn dt. And now we use our original equation. Okay, and we use this equation here. So once we take the derivative of this, we get this term, and then we have to bring everything to the other side. So we have this thing, yn minus 1, or let's see, yn, right, minus n minus 2t, ant, yn minus 1, plus all the way, or we could subtract all the way down to minus a0 t over an, or ant, like this, y0, or y1. All right, see? Yeah, because y1 is just y, right? So like that. So what I did is I just took everything here to the other side, and I divided by this term. All right? Okay, and this gives us the following differential equations. So we have this system of differential equations here, right? And this gives us now that, well, we can write this as a matrix. As a matrix. Slash vector equation. All right. All right. And so we have, so ddt of y1, y2, yn. So this is equal to some matrix here. So, and then we have y1, y2, yn. So y1 doesn't appear here. So we have something like 0, 1, and then it goes 0 all the way down to zeros like this. 0, 0, 1, like this, zeros. And then it continues down. So it's going to be like a diagonal, but it's above the first block, right? So it continues like this. Okay, and then this is the weird one. So here we have these coefficients. So let's see, sorry, this should be, so we have this coefficient here. This is the first one. So this one will be minus a0 of t over a(n) t. And then we have a1t over a(n) t, or not minus here, just a regular one, right? And then it continues to the an minus 1 term over a(n) t, like so. Okay? So, and right above this column, there would be a 1 here. So I guess I could put a 1. Then there would be zeros everywhere. So 0, 0. This needs to be like a little bit over. Let me put this. All right, and then we keep going down like this. Does that make sense? Okay, how you convert this into a matrix? So you have this. So now this tells us, this gives us our differential equation. d dt of y of t, this is a vector, is equal to at y of t. And so now this is a first order thing in many variables. Okay? So for the initial values, also change over. So here, y of 0, so this would be, well, this would be y1 of 0, y2 of 0, yn of 0, and then we were given those values here. So this was y0, y0 prime, right? And then we go all the way down to yn minus 1, 0, like this. Okay, and we're using the fact that these are what the derivatives are. Right, that we relabeled things as a derivative. Okay, so what's the point of this is that, solving, understanding linear differential equations, first order linear differential equations in many variables is just as hard as understanding higher order linear differential equations in one variable. Okay? So what's the point? Let me do an example then, too. So what's the point? So the point order linear ODEs in one variable are equally hard, equal in difficulty, to first order ODEs in many variables. Okay. So let's do an example. Okay? Okay, so let's consider the ODE that we've been playing around with this whole time, right? D squared y dt squared plus 2 dy dt plus 2y is equal to 0. All right? So let's convert this to a higher order system. So let's convert. So here, so note that here, a2 of t, this is just 1. a1 of t is 2. And a0 of t, this is also 2. Okay? So these are constant coefficients. But what I said applies generally. Okay? So now we'll let So we're going to so we change variables, introduce new variables. Okay, so so we had y1, so this was just y. Okay, and then we said dy dt. We said, I don't know how I did it. Y2 is dy dt. I forget which way I wrote it. I wanted it to write it the same way, but I forgot if I wrote the y1s on this side or the y subscripts on this side or the derivatives on this side. Do you guys remember? So I had like, I said something like convert, and then I wrote like a big list of things. There we go. Yeah, so let's do that. Let's do it the same way. So y is y1, and then dy dt is y2. Okay? So that's what I was doing before. Okay? So then now we can write down the differential equation. Write down the equations. Okay? So dy1 dt, so this was y2, right? Because this is just really d dt of y. And that's what we called this thing. Okay? So I'll put that in parentheses here. And then we had dy2, and now I dt, okay? So this is equal to, so this is like the second derivative, right? So this is equal to d dt of dy dt. That's what this is equal to. Do you guys see that? Okay, so now what I do is I just bring everything over to the other side, right? So this is minus 2 dy dt minus 2y. Okay, and so this gives us the system of equations here. dy1 dt is equal to y2, and dy2 dt, so this is equal to minus 2 y2 minus 2y1. Do you guys see that? Okay, and so these are what those negative coefficient things here we had here. Right? This is this thing. These are these minus signs that are appearing. All right? And now we can write this as a matrix equation. So I'm going to write this as that matrix up there. So we can write this now. Okay, so let's write it as a matrix equation. So here we have d dt of y1, y2 is equal to some matrix times y1, y2. Okay, so the derivative of y1 is y2, so I'm going to put a 0, 1 like that. Okay. And then we're going to have a minus 2 here. Minus 2, minus 2. Okay? So this converted, so we converted the ODE y prime prime plus 2y prime plus 2 is equal to 0 to the ODE, the first order system of ODEs. Well, I can write it like this. Y prime is equal to 0, 1, minus 2, y. Okay? So that's the point, is that we can convert something like this into something like this. Okay? And this is a first order thing. Okay. So, so one of the things that we can do, so, okay, this is a good question now. So now I think I've motivated why we're interested in systems of ODEs, first order systems. Okay, so one question is, so how do we solve? So let's say I'm gonna talk about with constant coefficients. Okay, and so so these are the following. So how do we solve? Systems. So we get something like dy dt is equal to a y. Okay, where a is an element C. So these are n by n matrices with constant coefficients. It turns out like the constant coefficient, okay, so what I'm going to say about the linear algebra, the constant coefficient thing matters. But if you did it with non-constant coefficients, that's kind of like as general as we want to go for like studying linear differential equations. So that's kind of like as hard as we want to go. Okay, so okay, so to answer this, I will give a so I need to review eigenvectors, eigenvalues. For matrices. Okay, and so let me just state some theorems. So, okay, so the theorem is the following. So let's. Okay, so not every matrix is diagonalizable. Not every matrix has a basis of eigenvectors. Okay, so there could be a situation where you could write down one of these, right, where you can't write down eigenvectors. Okay, so recall the following, so that so a matrix, so A is diagonalizable. Okay, so this is if and only if. So I guess you could call this the definition. So there exists a matrix E, n by n matrix. So A is an n by n matrix. So A is n by n. So let A be an m by n matrix. Okay, this is diagonalizable if and only if there exists a matrix E such that we'll have the following equation, matrix equation, okay, where D, well, it's going to be the diagonal lambda 1, lambda n. And so what does this mean? This means that it's like lambda 1, lambda 2, lambda n. Okay, and really it's zeros everywhere else, right? Okay, so so this is a matrix with diagonal entries. Okay. Okay, and this is if and only if. Okay, so this is the definition of what is diagonalizable. If and only if there exists a basis of eigenvectors. Okay, so for A. So in particular, c to the n, i.e. c to the n has a basis where each element of the basis is an eigenvalue. For A. Okay? And so the warning that I wanted to give here is a warning is that not every invertible matrix has a basis of eigenvectors. Okay, so there's an example. There's a classical example, right? You look at something like this, okay? This is a matrix that doesn't have a basis of eigenvectors. And in this situation, when you don't have a basis of eigenvectors, you can find so-called generalized eigenvectors, okay? So in this situation, one can find so-called generalized eigenvectors. Okay. All right. So, okay, and the diagonal matrix there gets replaced by what's something called the Jordan normal form. Okay. So, okay. Okay, so what's the general strategy of computing these things? So let's suppose that we have a basis of eigenvectors. Okay? So suppose how do we use eigenvectors to help us? So it's not always true, but I'm going to pretend it's true. All right? Okay? So the strategy is the following. So well, let's see. Okay, so if we have some eigenvectors, are a basis of Cn such that we have the following, so that A, C, G, let's say K is lambda K, C, right, for, let's say K is equal to 1, 2, up to N, all right? So to make this a basis, right, note that, so this lambda is not going to be 0. Well, I guess it could be 0 if it's a basis. So I guess we could still suppose that this is 0. Okay? So then what can we do? So then note that our E here, E over there, so the thing that makes it diagonal is of the form, let's say E looks like this. C1 C2. So this is the Greek letter C. So like, by the way, it's like XI. That's how you do it in LaTeX. Okay, and it's squiggle. Sorry, I don't know. It's kind of an inconvenient letter, but that's the letter I use for eigenvector. I don't know if you guys used another letter. Maybe capital K is what they used in the book before. But this is a pretty common one for eigenvectors. All right. It's the capital C is nasty. It's like, it looks like an E kind of, but it's an E, but without like, it looks like this, capital C. So I'm just going to use E instead. So capital C, have you guys ever seen a capital C before? It's like, looks like that, right? It's kind of gross. Okay, so let's not use that. Anyway, let me just keep it over here. Okay, so this is the change of basis matrix here that gives us, so this is the change of basis matrix that diagonalizes. Okay, so let me kind of show you how this works. I'm not sure if they show you how to do this, but so note that that A times this matrix E, this is A, and then we write the column vectors like this. I find this kind of presentation very useful when thinking about matrix multiplication. Okay, so when you multiply a column vector, what do you do with the column vector? You just take a column vector and then you do like this thing, right? Where you make sure you multiply the matrix. So this is actually going to be the new column of the new matrix will be like this. C2, A, Cn like this. Okay? So I found that when someone told me this, I thought that was very useful. Right? Now you can see kind of how the new columns look. Right? And this looks like lambda 1, C1, you know, so lambda 2, C2, etc. And Cn. Right? And you actually get, so we get that, so you can check this. So let's check what this thing does. Okay? So if we here, let's do EK. Okay? So EK will be this matrix. All right, this will be 0, 1, 0. And this thing will be the kth entry. Okay? So what is EK times, or E times EK? So what is just this part? So this will be E inverse A times something. So what is this thing? Picks out the kth what of this, the matrix E. So E is this matrix. So it'll just be CK, right? Right? It'll be the kth eigenvector because it'll pick out the kth column, right? So when you do that, it'll pick out the kth column. What is this thing here? So this thing is just lambda k. So this is E inverse lambda k times this thing. And so what does E inverse do? So this thing is linear, so we can bring out this lambda k, E inverse ck. Right? So this thing undoes exactly what this thing did. Right? It undoes this. So this will be EK. Okay? So this thing shows us that the diagonal matrix, this is why diagonal matrices and the bases of eigenvectors are related. So this shows that this thing, so this is this matrix. okay, because it acts on EKs by just lambda, right? Okay, so this shows that this shows you how the diagonalization is related to eigenvectors. Okay, so that's my point there. Okay, questions on this little trick here? Okay, we'll see it again. So eigenvectors show you how to diagonalize. How do we use this for ODEs? So again, back to this question. Feel free to shout things out. If my handwriting's bad too. Okay, how does this help at ODEs? I'm trying to go back to this question. So what we can do is, so normally, so given a vector, y, so what we'll do is we convert, okay, so let me show you let me just do something in symbols, okay? dy dt, like this, is equal to ay, right? This thing will convert to a system of differential equations, dwk dt is equal to lambda k wk, for k is equal to 1, 2, up to n. Okay, so we're going to take this and the diagonalization process is going to convert to a system of differential equations. So how do we do this? We write a general y of t. So this is usually y1 of t e1 plus yn of t en. So what we'll write this as in terms of the basis of eigenvectors. So here, y of t looks like w1 of t c1 plus plus wn of t cn. Okay, so what we'll have to do is we have to figure out what these guys are in terms of those guys. But once we write so you can always expand something in terms of a basis of these guys here. The basis of eigenvectors. So any vector can be written in terms of these eigenvectors. Okay? And so now when we plug this into our equation, what happens? So let's plug it into our equation. Okay, so this is kind of like the result, right? And then this is the explanation. Okay? So when we do this, right, d dt of y is equal to a of y. Okay, this becomes d dt of, now we write w1 of t c1 plus wn of t cn, like so. And then this thing becomes a w1 of t c1 wn of t cn, like so. Okay? And now this side just becomes w1 prime of t c1 plus wn prime of t cn. And then this side here becomes, well, we just apply a. A is a linear map. So these things are constant, right? A c1 plus wn of t a cn. Let me get out of the way. Okay. Lambda C1, lambda 1, lambda n, Cn. And so this gives us, so then we equate coefficients, right? Right? And so this gives us the system of equations like so. Okay, so I guess we could write dot, dot, dot on the other side too. And so this is our system of equations here. So by diagonalizing, we reduce to these really basic equations like so. Right? And actually, so let me stop there for a second and let you guys. So in practice, what will happen is you'll actually have these things here, right? And then you'll be able to write out what this thing is, right? Because this thing you'll be able to solve, right? So this is the explanation. But you can solve this system of equations really easily to get your solution. So the general solution looks like here. So it looks like, so W1 looks like some constant times e to the lambda 1t. W2 is some constant e to the lambda 2t. So let's say ck's are constants, right? And then to make it a real solution, you have to do that Euler's formula thing, okay, if you're interested in real solutions. Okay, so in particular, y looks like c1 e to the lambda 1t c1 plus c2. So it's a linear combination of these basic solutions, like so. Lambda nt c n, like this. Okay, so this is what the general solution looks like. Okay, so to actually compute this, right? So let me stop for a second and let you guys catch up. Okay. Okay. So computationally, these coefficients are solved for. The lambdas and the c's come from a matrix computation. So the lambdas and these guys, c's come from like doing linear algebra. Okay. Well, I guess they all come from doing linear algebra. From a computation involving the matrix. Which we haven't done yet. A. And the C1s, the C1 through Cn, come from initial values. Okay, so if someone asks for a general solution, you can leave those as like arbitrary constants, or you could actually solve for them. Okay, so maybe we should do one in practice, right? Okay. So let me just start to do one, okay? Or let's see. I guess I could say a little bit more about how to compute the eigenvalues and eigenvectors. So how to compute eigenvalues and eigenvectors, and then we'll do an example next time, and then the time after that we'll have the quiz. Okay? Okay. So so how to compute the eigenvalues and eigenvectors. Is it clear as to like why we want to do this now? It's like any constant coefficient linear differential equation, however many order, reduces to this problem. Okay? And now if we can find eigenvalues and eigenvectors, we reduce the whole problem to finding linear differential equations. These not linear, but these like stupid differential equations, right? These really, really stupid ones, right? Okay, these are really easy to solve, right? They're just exponentials, okay? And then once we do that, we can write down the general solution like so, okay? So this allows us to solve any differential equation like this, okay? So all that remains to do is to show you how to compute eigenvalues and eigenvectors, and then we're in business for computing solutions, okay? So how to compute eigenvalues and eigenvectors. So I'm going to tell you the procedure, and then next time we'll do examples. Or if you remember to do it, you can go ahead and do the homework. Okay? So what we do is that so we note that, and again, this doesn't always, so it won't always work because we have this like problem with these generalized eigenvectors, right? So sometimes there's matrices which aren't diagonalizable. Okay, so if someone off the street came to you and they're like, hey, I got this matrix, will you help me find the eigenvectors of it? Do not trust them. I mean, you can trust them, but it's not always true that you can find the eigenvalues and eigenvectors of a basis completely. Okay, so beware. Okay? Okay, so, but if, we do have an eigenvector, right, then the matrix, then this thing here, A minus lambda I, so here is the identity matrix, this is 0, okay? So in particular, this guy is in the kernel of this matrix, right? So this tells you that this thing here, this vector, this eigenvector, is in the kernel of A minus lambda I. Okay, so in particular, we need to find the values of lambda so that that's a singular matrix, okay? And you recall that a matrix is singular if and only if it's determined as 0. So we find the values, the lambdas, where this thing A minus lambda I is singular. So this is what's called finding the characteristic polynomial. So we have this. If and only if A minus lambda I is singular. Okay, so this gives you a polynomial. This is the characteristic polynomial. Of the matrix A. Okay? So we can actually solve for the roots of that thing, right? So maybe at this point, like, it could be complex roots or something, right? Okay, so then what do? We find lambda, solving the above, a root of the characteristic polynomial, right? So what do? We compute the kernel of the matrix. So this is a fixed one now. So this is kind of like a general thing. And now we take a particular solution of this, right? And we compute the kernel of here, a minus lambda I. Okay, so in particular, this involves solving the equation. So this means solving that a minus lambda I, something like this. So then we have like, now I need some names for the coordinates. So let's say C is equal to 0. But this is actually comes down to something like a minus lambda times the identity. And then you actually have to write it out. So like, let's do x1 through xn. So you actually have to find what those are, okay? And maybe it's two-dimensional. Maybe, maybe it's, you'll have some free parameters there or something like that. Okay, here. So this is the thing that you need to solve, right? Okay. All right. So, okay, so then next time I'll do some concrete computations with these. And we'll get some bases of eigenvectors and solve some differential equations. Okay? All right.